Welcome to what I'm going to call the most important chapter of hor166. This is where we're going to lay the groundwork for all the mathematical analysis of soils that will help you better understand and use them in your turfgrass career. First, we're going to talk about soil texture. Soil texture is the size of the soil particles. We're going to talk about the soil triangle. We can have sand, which is the coarsest of the soil material, silt, which is in the middle, and clay, which is the finest. The proportion of these three things can be in any sort of proportion, half, 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 50, you'll see on the soil triangle, but whatever that is, it's going to affect the internal surface area, the water holding capacity, the CEC, which Ms. Westman talked about, which is the cation exchange capacity, so that's the available nutrients for the plant. And this is done by the size of the soil pores in one respect. Macropores are the pores in the soil that are filled with air, very important for respiration, so the plant can grow and use the sugar that it makes in its leaves. And micropores, the water holding capacity that are important for the plant to get water it needs to do photosynthesis. Micropores can be a detriment to the plant if there are too many because they limit the amount of oxygen that can get to the roots, and we're going to talk about that quite a bit as we move through here. So water is one of those things that the plants need. You're out there syringing, but we tend to err on overwatering because it's less of a penalty than erring on underwatering. And as an educated turfgrass professional, you're going to need to fight against overwatering. So here's a representational soil particle. You can see we've got a clay particle right in the middle, very small. Then we've got our silt particle here, and then from this size to this size. So the range of size for sand is very big. Anything bigger than that is going to be gravel, and we're not going to use it. It doesn't really act like soil as much, but a small amount of these small particles will greatly affect the physical properties of soil. So here's just another representation of that. This would be a finer soil. This would be a coarser, more coarse soil. So as we move from fine, more water holding, to coarse, more air holding, you can see all the air spaces in there. We're going to change the soil physical properties. I'm not going to dwell on this very long. You can look at it. It's important to know that as the diameter of the particle size goes down, the surface area for the same square area goes up. So clay is going to have a diameter below 0.002 millimeters, but it's going to have 8 million centimeters squared of surface area in 1 gram. And 1 gram is about the weight of a paperclip. So you can see going from that big sand grain has a surface area of 11 centimeters. That's if you took the round particles and flattened them all out. And we're going to talk about that greatly in the next video when we talk about putting greens. So here's our soil triangle, and you're going to need to learn to read the soil triangle. This is very important, and we will work on this in class. And if you don't understand this, you need to come see me and talk about that. So if this area here, if a soil has more than 86% sand, and it can have upwards of 10% silt or upwards of 10% clay, it's going to act as a sand. So it takes a great amount of sand to have something act like a sand. If something has even 50% clay, it's going to act like a clay. So let's take a soil, let's take something that's 20% or 25% sand, and that will go up there, and it's 30% 30% silt it is going to act like a clay because it's going to have 45% clay. So that would be that soil. And you only need 2 parts. And we're going to show you how to do that in lab, how to measure how much sand, silt, and clay. And it works nice because they're particle sizes and they settle out a solution at different rates. So spend some time on this. You will have questions on the exam that ask this. The exam will not have these arrows or the percent silt there. But you can figure that out because obviously sand along this axis, if something's 100, it would be sand. If this is 100, it'll be clay. And this is 100, it'll be silt. So they act like what they are if they're there. But if I'm a farmer, I want sandy clay loam. That's kind of where I want to have my increased yields. Clay is going to be too hard for the plants to grow through. Sand is going to be too drouthy and not allow enough moisture in for the plants. So that's one of the things we fight in a USGA putting green is the excessive moisture. So this slide just lists some generalities. Fine soils are going to retain nutrients and water more. Clay is harder to work, to move. Friability, we call that, the ability for equipment, plows to get through it. When we're building a golf course in the sandhills, we can use very light tracks. When we build a golf course up in northern Massachusetts or in the Piedmont, we need really strong pans and much different techniques. So it's much more expensive to build a golf course in clay than it is in sand. Coarse soils are going to have much more airspace and are going to be easier for plant roots to grow through if there's moisture there. So that's a balancing act. Coarse soils are going to have low nutrient holding capacity. Loam in between, a little bit of both, is going to be your best place for yield. And yield is something we think about in corn. Yield is bushels of corn, but there's a yield for turf grass. Yield for turf grass is the grass clippings in the basket. And sometimes yield is not something we're going for in turf grass. So if we want to modify soil texture, which we often do in turf grass, a little bit of clay will surround a sand grade and eliminate any benefits of that sand. So small amounts of clay affect soil physical properties greatly. Organic matter, which we're going to talk about a little bit later, which is dead, dying plant material, will make sands less drouthy and loosen a clay. So organic matter is going to be your friend in a lot of ways. We don't want excessive organic matter. We don't want it layered, which could cause black layer, but we do want small amounts of organic matter will make the soil properties better in a lot of situations. Not every situation. So here's where we get into the math. Soil particle density is the definition. That's the solid particles only. So that's if we could eliminate all air and water, what would the soil's density be? And density is always going to be grams per centimeter cubed. Quartz, that's one rock. The particle density of quartz is 2.65 grams per centimeter. Water is 1 gram per centimeter. So that's a number you need to put in your head and memorize. That's very important. So if a soil has a bulk density, and bulk density we're going to talk about next is the density of the soil with the airspace. We dry it out so that there's no water in there. And if the density of soil is less than 1, it would float. So there are some organic soils that will float, but most soils are going to be greater than 1 in bulk density, and all soils are going to be less than 2.65 in density, because if they were 2.65, they'd be a rock. They'd be solid. Clay is between 2 and 3 grams per centimeter depending on the type of clay. So that falls right near 2.65 also. Feldspar, which is another clay, 2.5 to 2.7 grams per centimeter, so their 2.65 is within that range. So the number to remember, 2.65, is the particle density of soil. And that's also the particle density of rock. If we were to do lead, lead would be PB, much heavier than that, but we're not. There's not a lot of lead in the soil. So soil is predominantly silica. Silica is quartz. So there, here, next slide, we're on to bulk density. Bulk density is the density of actual soil. It's going to be less than the particle density, always. If you do this math and you have a bulk density greater than your particle density, you've made a mistake. Bulk density is the weight of the dry soil. So that's the soil put in an oven divided by the volume of the dry soil. It's going to be grams per centimeter cubed, and the range is going to be between 1 and 1.8, unless it's an odd organic soil that floats. So this, you need to know how to do these. We're going to calculate bulk density, and by knowing the bulk density, we can figure out the moisture percent. And the moisture percent is going to be important. Every week you're going to have to report the moisture percent of your project. There's Mike Philo, superintendent at Charlotte Country Club, and he's out there looking at the soil with his soil probe, and he can get a good feel for how much moisture is in his soil because he knows quite a bit about bulk density. There's a bulk density of 1 would be a much more open soil than a bulk density of 4. A more compacted, or 1.4, excuse me. The higher the number, the more compacted the soil is. Porosity. Porosity is a percent. It's going to be the percent of total air and water space in the soil. So if we dry out the soil, we can calculate this because we know it's going to be the difference between the particle density and the bulk density. So 100% minus the bulk density divided by the particle density. Remember, the bulk density is going to be smaller always than the particle density, times 100 will give us the percentage of pore space. And it should hopefully be around 50%. Or we can take the wet weight of the soil, which is completely wet. So this is saturated, and this is something that's difficult to do. This has to be done in the lab, and it has to be done over time. So we have to wet the soil completely, minus the dry weight, which is the weight of that soil put in an oven, so all the water is reduced. So that's basically the wet weight minus the dry weight is the weight of water. And because the water has a density, particle density of 1, we can divide that by the soil volume, which is centimeters cubed times 100, and that should give us the same number as the porosity. So you need to do a little bit of wrangling around with this to understand that. But that magic number 1 gram per centimeter cubed, allows us to cancel out and get 0. So there's no units on this. The units are percentage, and this gets some students confused. So units for particle density are grams per centimeter cubed. Units for bulk density are grams per centimeter cubed. If you're getting porosity, you need to cancel out all those units. And these are good numbers to have and be able to use. We'll give you these formulas, or you'll be able to have a sheet with these formulas on the final exam, but you need to be able to use them, not to memorize them. But you do need to memorize the formula for bulk density and particle density. And here's TJ, one of our former students. He's figuring out the bulk density of this gravel. And that's a good exercise, and we'll do something like that. We'll bring in some stuff and figure out bulk density and particle density of the soils that you're using for your project and something else. So another visual, take some time and look at that, read it. I'm not going to read it for you. Again, by knowing the porosity, it doesn't tell us much about the pore size. And we're going to talk about the ideal representation, this perfect soil, which is 50% solids, 25% water, and 25% air, as we move forward. It's in reality, we can get pretty close to that. So, the next concept I'd like to introduce, and we're going to talk about it in our USGA lecture next, is the rate at which water moves through soil. Texture influences that. So the more coarse the texture is, the faster the hydraulic conductivity is. And hydraulic conductivity is usually expressed in inches per hour or gallons per hour. And what we do is we set up the soil with a constant head of water on top of it, and we measure how much water goes through the soil at a certain time. So it's a rough measurement. It depends on how the soil is packed. It depends on how many wormholes there are, how many channels of macropores. A channel of macropore will have water move quickly through that. But generally, sand is going to be fast. A clay is going to be slow. Sand will be very fast. And then our silt will be more moderate. And then as you move around, so as you go higher in the soil triangle, hydraulic conductivity is going to slow. The fastest hydraulic conductivities are going to be right down here in coarse soils, and a gravel would be even higher, almost unmeasurable. It would be so fast. So that would be inches per hour would be a way to think of hydraulic conductivity. You need to remember that hydraulic conductivity has nothing to do with slope. We're not going to get lots of infiltration of water on the slope because the water is going to move off over the slope. But if we have an area that's a puddle down here, infiltration rates will be faster. So in the golf course we had another dynamic, which is surface drainage, and something that Ross did is drain his greens in at least 3 different directions, and this is a good example that drains in almost all directions. The Donald Ross turtleback greens, which make wonderful putting greens, but they also really help with drainage, surface drainage. Macropores are large, contiguous pores that hold air, oxygen, water, all the things that's in the air that we breathe. Micropores generally hold water at field capacity. As the soil dries, the larger micropores will become filled with air. So field capacity is when the macropores are filled with air and the micropores are filled with water. It's something that's measurable, but the soil is always changing. The soil is always either wetting or drying, and we'll go through some videos of that, which I think should help you understand it. But field capacity is another definition, and what you need to know now is that field capacity is when the macropores, the big pores, are filled with air, and the small pores, are filled with water. So, on to the math that we're going to need to do. You're going to need to figure out the moisture content of your soil every week on a weight basis, a volume basis, and a soil depth basis. So the weight basis, you're going to take the wet soil minus the dry soil divided by the dry soil times 100 will give you how much water weighs there. So the dry soil will be a constant. We're going to dry out our soil and weigh it, the volume. Once you dry a soil, you ruin it for plants. But we'll dry a different volume, and then we'll use that so you'll know how much weight of water you have. On a volume basis, you take the percent of water, volume. So this weight basis times the bulk density divided by the density of water, and the density of water is 1, will give us how much volume of water we have. And then the soil depth basis is if we could smash out all the water in a soil core, a 12-inch soil core, how many inches of it would be water, and ideally we'd like that to be 25% or right around 3. So if we take 12 inches times the percent water by volume basis, so we need to use this to get this to get this. This will give us that we have 3.24 inches of water. And you need to, this is an important slide, you need to write this down, maybe stop it here and work through some of these, and we'll work through some of these in lab to help you understand. And that's why your soils have to be measurable with the scale that we have. So that's why they have to be of the size that they are going to have to be for the project. Soil structure, PEDs are natural soil structure, clods are from tilling. That's when soil will tend to aggregate. We have this area, the soil is forming a structure and leaving big air spaces. So the tighter stuff will come together. Shrinking and swelling forms PEDs. If you go through and till something, when it's wet, you'll form clods, and everybody's seen that in a clayey soil. And that's not so good for the plants or turf grass. And that's something we're not going to worry about a lot in turf grass because we're generally dealing with sands, and sands are generally a structureless soil. They're going to be more permeable, and infiltration and aeration will be greater on a sand than non-sand soils. Some soils we would consider massive, very large soils. Fine soils stick together, a clay. Some of the lower horizons will do this, as we talk about the A horizon is the top, the B is right behind. So underneath the B horizon, where lots of nutrients accumulate down below where the plants can get it, can be considered massive. Sometimes these will be a barrier to water moving, and tilling wet soil may cause the soil to become a barrier for water to move through. And this can happen in turf grass sometimes. If we were to use solid aerification tines over and over again at the same depth, we could create a plow pan, and this would also make a massive soil layer that didn't allow water to get through. To form structure, grass roots will form structure even in a sand. Freezing and thawing form structure. The hyphae from actinomycetes and fungi, kind of like the roots of fungi and actinomycetes, and then iron, some chemical reactions. So structure is helpful. Sometimes it will improve soil structure. And I want you to think about what ways could you improve soil structure on a golf course. What do we do to change the structure of soils? Think about that for the next lecture and for class. So, compaction's a bad thing. When aggregates are pushed together, bulk density is going to go up. Pore size is going to go down. Crushing those aggregates, those things that have formed looser soil, soils where on the Great Plains you used to be able to take a broom handle and push it down 3 feet. Particles are pushed together. Compaction is a bad thing, and we fight that with aerification. Solid, hollow tine aerification is the best way to fight compaction. Bulk density, higher bulk densities than 1.4, we're going to have to do something about that, some sort of mechanical cultivation to decrease the bulk density. So, macropores, if the soil is compacted, will we have more or less macropores? Think about that for a second. They will be decreased. So air holding space is reduced with compaction. Porosity decreased. Bulk density increased. That one should have been easy. Aeration will be decreased. Water infiltration decreased. So you need to have a good working understanding of what compaction does to these 5 different properties and more. How does compaction form? Wet soil compacts quicker than dry soil because it's lubricated. So you don't want to till, irrigate, drive out on soils when they're wet. And that's part of one of your ammunition when you want to keep carts off the fairways when they're wet, is because compaction happens much faster. But something that people don't often think about, if we've got a tractor, a 1,000-pound tractor, or and this is always a fun section because I like to pick out somebody in the class and ask what their girlfriend weighs. But let's pick on Mr. Quinn and say I've seen pictures of his girlfriend and say she weighs about 100 pounds. In a 1,000-pound tractor, Mr. Quinn's going to drive a 1,000-pound tractor across the putting green. He got a little crazy. And his girlfriend's going to walk across the putting green in 1-inch high heels. Who's going to do the most damage? I want you to do some math on that. And it's very easy math. We take 1,000 divided by 18 inches is going to give us 55 5 psi. psi. And you guys need to be able to do that. 1,000 divided by 18 pounds per square inch. And Mr. Quinn's girlfriend is going to be 100 pounds divided by 1 square inch is going to be 100 psi if she's walking on her high heels on the putting green. So obviously she's going to do a lot more damage than a tractor with turf tires that have a padding surface area of 18 inches. So you need to be able to do this math. It's pretty easy math, but it's interesting to see how just by spreading the load we can decrease the compaction that's going to be in one area. So a plow pan or till pan can be caused in turf if we're not careful from those heavy equipment, and also from solid tine aerification. It's pushing the soil down underneath. It might be lowering the bulk density at the top, but it's increasing the bulk density at the bottom. One little oddity of this whole thing is sometimes a little bit of compaction can increase yield. Sometimes there's too many air spaces, and if we give a little bit of compaction in a field that's really open, we'll make available more water and more nutrients for the plant. Temperature of soil is another thing that's interesting. And know it takes 5 times more energy to warm water than to warm mineral particles. So sand soils, like we have in Pinehurst, like the soil here on the right in this picture, is going to dry out and warm up much faster than Piedmont soils, this red soil, the clay, more clay soil here on the left. So you want to think about what's going to happen in the coastal plains, which is here, versus the Piedmont. Piedmont soil here, coastal plains here. I'll give you a hint. In the springtime, where does the grass get greener faster? And you need to know that for the final exam. And you need to ask me if you don't understand why your answer comes out to be sandhills is a much easier, faster place to grow grass. Crabgrass will germinate faster on warmer soils. We can mulch, as Ms. Westman talked about greatly. Cool season grasses root at 85 degrees Fahrenheit. So soil temperature affects a lot of different things, and there's natural points, times, temperature dependent. Crabgrass will only germinate at certain degrees under certain conditions. One of the big battles in turfgrass is fighting that crabgrass. The darker a soil is, generally the more organic matter there is. Bluish gray soil indicates soils with no oxygen. I'll show you some pictures of that. And then here's our question of the day, and we'll talk about that in lab. Why are wet soils darker than dry soils? And then here's a picture, a nice sand, Pinehurst. Here would be our A layer. Organic matter's been put down by plant roots. And then we get into our B layer, where things are moved through with water, and then the C layer in here where nutrients start to accumulate. This would be an anaerobic soil. I talked about that gray soil. This would be from a bog. No oxygen is in there. So oxygen is not the terminal electron acceptor. The bacteria that live in these soils use sulfur, and that's why we have what my daughter calls pig mud. So the smell of anaerobic soil is the smell of those bacteria doing their job, using sulfur as the terminal electron acceptor for respiration instead of oxygen like we use, in most of the plants that we deal with use oxygen for that.